much for the invitation, and thanks everybody for joining. I would encourage you, to jump in and ask questions. So this tutorial has two parts. I'll start with talking about fair allocations of indivisible items when agents have equal entitlements to the items. And then in the second part, Uri will talk about the case in which agents have arbitrary entitlements, potentially unequal. Okay, so let's start with divisible goods. So divisible goods, we want to divide divisible goods among agents that have equal entitlement without using any monetary transfers. So usually we model such goods as cake. We want to partition the good in some fair manner. And so here is a well-known procedure to do so. Say we have two agents, so one of them will cut and the other will choose. So think about this cake as a non-homogeneous cake, heterogeneous cake. So the cut is going to be somewhere, and the cutter will probably cut it in the middle, assuming that the other agents will choose, say, adversarially. So one is cutting to equal pieces, the other pick a piece, and then both agents get at least half the value of the cake from their own perspective. So this kind of allocation has a very nice properties. It's envy-free and proportional. So what's envy-free? Each of the agents is happy with the piece that she got. So the cutter is cutting to equal value pieces, so she doesn't care which one she'll get. And the chooser is picking the best of the two. So each one of them doesn't envy the other. And it's also proportional. So we define the proportional share of an agent to be 1/n fraction of the value of the cake. So here with two agents, it's half the value of the cake, and each one of the two gets at least half the value. The chooser would of course pick the better half, and the cutter would cut equally, so she will also get half of the cake. And this can be extended to 3 agents, it can be extended to n agents. But we are actually going to talk about the more challenging problem, or a different challenge of indivisible items. So how do we partition indivisible items in a fair way? Okay, so now we have a bunch of items. So here we have an example with 3 items. Each one of them is indivisible, so we cannot share the ball or split the ball to 2 parts. And then the agents need to decide on a partition of the items between them, and both have equal entitlements to the items. Now the proportional share of an agent is still 1/n value, 1/n fraction of the value of the entire set of items, m. And clearly we cannot always find an allocation that is proportional. Think about the case in which both agents just want the ball. It won't help giving any of them any of the other items, so there doesn't exist a proportional allocation. And of course, also there doesn't exist an envy-free allocation. So that's an example of an allocation, and if both of them only care about the ball, this of course is not proportional or envy-free. Okay, so let's talk about a few examples of this problem. So first is the allocation of slots in highly demanded courses in university that have limited capacity. So usually you don't pay to get those electives. Second is maybe dividing the housing unit to eligible residents by the government. Another is dividing items of sentimental value in an inheritance between the different heirs. Allocation of offices in a building between different departments in a university. So the items are the different offices and they cannot be split, and there is no payment involved. And there are other examples. Okay, so let's talk a little bit about envy. If we just give the item to one of the agents, maybe that would be fair ex post, because ex post, nobody can actually expect to get the item, but it's not envy-free. So one agent would definitely envy the other agent. And of course, when you have only indivisible items, we cannot find an allocation that is envy-free and proportional. So we say that the proportional share is not feasible, meaning that for some valuations of the agents, we cannot find an allocation that both of them will be happy and given at least the proportional share. Of course, once we have a single item, we cannot get ex post fairness, but one can think about ex ante fairness. So we might toss a coin to decide, for example, who will get the item. And you can think a little bit about how we can use coins to get fairness. And I'll talk about that at the end of this talk. But just as a teaser, think about these two agents dividing 11 candies between them. One of the random options to do that is maybe toss a coin who gets all the 11 candies, and consider your kids and think whether they would consider that as a fair allocation. Okay. So clearly, when we want to divide items fairly, the main question is what is fair? And we can think about various ways of defining, obtaining this goal of dividing the items fairly. So the first is maybe we come up with some procedures that is fair. So this, I'll call that procedural fairness. For example, if the procedure is, say, discriminate between different agents and give priority to one over the other, one might argue that that is not fair. So we can look at the procedure and consider whether it's fair or not. Second, we can think about ex ante fairness. So we want to come up with some distribution over allocation of the items that is fair under some definition. For example, the proportional share can be obtained ex ante by tossing coins and deciding who gets all the items. So that would be an ex ante fair allocation. And then there are ex post notions of fairness, in which we think about fairness of the final allocation, so the assignment of the items at the end of the game. And for ex post fairness, there are actually two lines of thoughts. So the first line of thought is thinking mainly about envy. So envy freeness, of course, cannot be obtained when items are indivisible. So we'll talk later about the other notions that are relaxed version of envy freeness, for example, envy free up to one good or envy free up to any good. And we'll discuss that later. A different approach that is the main interest of this tutorial is trying to think about share-based fairness. That is, each agent only care about the value of the bundle that she gets, and that doesn't care at all about how items that she did not get is partitioned between the other agents. And she think about what she deserved, and we want to give her what she deserves or close to it. And we call that share-based fairness, and that would be the main focus of most of this tutorial. Okay, so let's be a little bit more formal about the model. We have a set of n agents. We have a set M of M indivisible items. I'll sometimes call them just goods. And we have no transfers, so we cannot actually compensate agents with money. And each of the agents has evaluation functions that maps subsets of the items to a number, which represent how much she values that subset. And most of this talk will focus on the case of additive valuation. So the value of a set is just the sum of the values of all the items in the set. And in the first part, I'll mainly focus on the case in which items are goods. That is, the value of every item will be non-negative, and therefore the value of every set under additivity will also be non-negative. And when we think about deterministic or ex post allocations, we will be looking for an allocation which is just a partition of the M items to n disjoint bundles, where agent I gets bundle AI, and we want that partition or this allocation to have some fairness properties. Okay, so let's start by trying to generalize this cut and choose procedure from the cake to the case of indivisible items. So we can think about two agents here with three items. They have additive valuations over the items. So in this example, for example, the blue agent has a value of 10 for the books and 9 for the bell. And she needs to cut, and then the red will choose. So she will cut in a way that will try to partition the items as equally as possible. And then the red will choose a set. So that's cut and choose when items are indivisible. We can also think about envy-free notions. So here we have an example with, say, 5 identical items. Clearly, when we have two agents, one of them will get more items than the other. But this allocation, this allocation has the properties that is, while it's not envy-free, it is envy-free up to 1 good. So what does it mean? It means that after we remove one of the items from the red set, then the panda doesn't really want that set over the set that the panda got. So each of the agents doesn't envy the other agents if we remove one item from the other set. And envy-free up to 1 good is the case in which we can remove, say, the best item. Envy-free up to any good, or EFX, is the case in which we are only allowed to remove the worst item or any item. Okay, so there is a procedure that always finds an EF1 allocation, and that's very nice because we have existence of an allocation that is fair in some sense. It's an EF1 allocation. Okay, so here is a procedure for additive valuations that is EF1. We have a set of items, and then we let agents, we pick some random order over the agents and let agents pick the items, whichever items they want out of the remaining items. So maybe blue will pick the diamond, and then red picks one, and they keep on picking, and then after each one of them pick one item, blue picks a second item, and then they continue picking till the end. And we can see that this allocation is actually not envy-free, of course, but it's envy-free up to 1 good. And why is that? So clearly, blue doesn't envy any one of the other agents. She always gets the best item out of every 5. But if we look at purple agent, the purple actually might envy blue because blue chose an item before her. But know that if we start this procedure from the bell, then actually purple is always picking before everybody else. So up to the first item that was chosen before the bell, purple doesn't envy anyone else, and same argument can be formalized to prove that this allocation is envy-free up to 1. Okay, so we have an allocation that is envy-free up to 1 good. Let's try to think how agents will behave, say, in this round-robin procedure. So what do we expect the agents to do? The procedure expects them to actually pick items according to their order. So, blue will pick first, she will pick the books, and then red will pick the bell, and then blue picks again, and then blue ends up with value of 12. But if blue actually knew that the valuation of red is as listed, clearly this is not optimal. So if she picks strategically, actually she's better off picking the bell first because the bell has high demand. Also, the red agent wants it. And then red will pick the apple, blue will pick the books, and blue will end up with a higher value of 19. So we see that actually if blue picks strategically and actually she knows the value of red, then she can improve her valuation. But we are going to actually think about safe strategies for the case in which blue doesn't know. So if blue doesn't know, then she wants to play a strategy. We are going to assume that she plays a strategy that will guarantee her, the best possible bundle in the worst case. And in that case, actually, what she should do is pick in order, because the worst is actually for the red, to actually have the same valuation and always pick the items that actually blue wants. So in this case, in which agents are risk averse in a sense, and they don't know how others evaluate the items, then they would pick in order. Okay, so we have a very nice procedure, the round robin procedure, that gives us an EF1 allocation, so maybe everything is solved. So let's look at another example. In this example, we have n agents, in this case, n equals 5. And we're going to have n minus 1 really valuable items. These are the diamonds. And we have n items that are much less valuable. These are the rocks. And think about the case in which one diamond equals to n rocks. So if we run the round robin procedure, each one of the 4 first agents will each pick a diamond. Then the purple will pick a rock, but then the round robin procedure dictates that we actually start over, and purple ends up with just the rock, while everybody else end up with a diamond and a rock. So although this procedure is actually EF1, so note that once we remove a diamond from each one of the other sets, then purple does not envy that set anymore. While this is EF1, actually purple will complain. She will claim that actually she got only value of n plus 1, of only value of 1, while everybody else got a really high value of n plus 1. And she might come and actually suggest the following. She would say, let me actually partition the items to n sets and let you all pick first, and I'll be left with, whichever set that you leave me with. And we can see that in that case, actually purple will get a value of n. So this idea actually is generalized to what's called the MMS. So the MMS defines the max mean share of an agent. The max mean share is the highest values that she can guarantee herself by splitting the items to n bundles and getting the worst one. So let's look at this example. Let's assume that there are n equals 3, and we have a panda with this additive valuation over the 4 items. And she's asked to partition the items to 3 in a way that she, knowing that she will get the worst one, she would, of course, partition like that. And then her MMS equals 2, because that's the value of the least valuable items in the best partition that exists in that case. So this is the max mean share, and that's a very nice share. Of course, we cannot give all agents more than the max mean share. Think about the case in which every agent has exactly the same valuation. Then by definition, the max mean share is the maximum that the worst agent will get. Okay, so can we always find the allocations that give every agent her max mean share? So let's start with 2 agents, and let's realize that actually we have seen a procedure that ensures the max mean share. That's the cut and choose procedure. So let's assume that the blue cuts and then red chooses. So blue would cut according to her max mean share, then red will choose a bundle, and we can see that red would choose the better of the 2 bundles. So if she's going to get at least half of her value, that's her proportional share. And when agents have additive valuation, that proportional share is at least as high as the max mean share. So red gets her max mean share, and blue, of course, gets her max mean share because she either gets the worst of the 2 bundles or the better of the 2 bundles. So both of them gets their max mean share. And note that this proof actually heavily relies on the additivity of valuation. So if we think about other valuations, we'll see that the situation is different. Here with additive valuation, it's actually better to be the one that chooses. But let's see an example in which once we move out of additive valuations, actually it might be better to cut. So think about the following valuations. One of the agents just wants, there are 4 items, and one of the agents wants bundles of items of the same color. So you get value of 1 only if you get both black or both purple items. while the other agents like identical items. So blue actually likes either both apples or both bells. And of course, if blue let red cut and then chooses, she'll get 0. So in this situation, when valuations are not additive, it is actually better to cut and not to choose. Okay, so let's now go back to the MMF and ask, can we always give every agent her MMS? And the wonderful paper from 2018 by the 3 authors proved that even with 3 agents and additive valuations, there are valuations in which we cannot give every agent's her MMS. And note that clearly those valuations are different. So for equal valuations, we can give any number of agents each her MMS. So we have this situation in which once we move from 2 agents to 3 agents, we cannot longer give every agent her MMS. And this is in contrast to divisible items in which we could, for example, give every agent her proportional share. So, this again shows the difference between indivisible items and divisible items. Okay, so the MMS is not feasible. We would argue that for fairness, we must use a feasible share because if the share is not feasible, this means that we cannot guarantee every agent that she will get at least her share. So we need to consider other shares. And I'll define briefly, in a minute, I'll define what do I mean by other shares. But informally, we can think about a situation in which there are multiple shares and each agent would pick her favorite share, right? Would argue that some other share should be used in order to obtain fairness. And the question is, can all agents agree on a feasible share that is best for everybody? So if they can find one share in which everybody would be happy, the share is maximal, in some sense of maximal value for each one of the agents, then they could agree to use that feasible share. We saw that the MMS is not feasible, so they cannot use the MMS. They will need to find some other share to agree on. And if we can find such a share that everybody agrees on, then that share could be used as the fairness notion. Okay, so let's formalize the notions of shares and share-based fairness. So the most fundamental fairness principle that we are after is that identical agents should be treated equally. So what do I mean by that? So let's look at the definition of a share. A share is a function that maps the valuation of the agents and the number of agents to the non-negative value S of Vi and N. And crucially, this function is anonymous. So we don't index this function S by the name of the agents. So this actually captures the fact that it only depends on your valuation and the number of agents. And if there are 2 agents with identical valuations, they should be treated exactly the same. So that's a share. Is there any questions about shares? I'm running fast. Please stop me if you have any questions. Okay. So we have defined a share, and now we can formalize what we mean by a feasible share. So a bundle B is acceptable to agent I for the share S if the value of the bundle is at least the value of the share. So the agent got a bundle in which her value is at least the promise that she has, the share promise. And now the share guarantee, if an agent looks at a share, the agent can ask, how much am I promised to get with that share? The answer is the share guarantee. That is the minimal value of any acceptable bundle. And now an allocation is acceptable if all agents accept the bundle that they got. And the share is feasible if for every valuations of the agents, we can always find an acceptable allocation. So we have seen that the MMS is not feasible because for some valuations, we cannot find an acceptable allocation. and therefore it's not feasible. Okay, so let's look at the landscape of all shares. We discussed the proportional share and the max-min share within the landscape of all shares. And now we are going to focus on feasible shares. These are shares in which we can always give every agent an acceptable bundle. We saw that the proportional share is not feasible. The MMS is also not feasible. But the MMS is at least as good as any feasible share. As we discussed, if all the valuations are identical, we cannot give every agent more than the MMS. Okay, so we're searching for a feasible dominating share that is a share that is better than all other feasible shares. So can all agents agree on one feasible share? If we can find kind of a best possible share, then they would agree and use that share. So we say that share S dominates share S prime if the value of the share S for every valuation is at least the value of S prime, and we're looking for one feasible share that dominates all other feasible shares. So does there exist a feasible share that dominates every feasible share, say for the class of additive valuations or for other classes? So let's go back to our shares. Can we come up with some feasible shares? So, the zero share is clearly feasible. All of the agents would agree that that's quite a lousy promise just to get zero. So here's another share that is a little bit more interesting, the value of the nth best item. So we saw that if you think about the round robin procedure, in the round robin procedure, each one of the n agents will get value of at least the nth valuable item. So this is clearly a feasible share. We can promise all the agents that they will get value of at least the nth most valuable item. And this share is better than the zero share. So it dominates the zero share. Now we can keep searching and find other shares that might be better. So here is a share that is actually better, and everybody would agree that they prefer it over the nth most valuable items. This share is either the value of the n-1 item or the value of all items from n and onwards. So this share is always better than the value of the nth most valuable share. So all agents can agree to move to that share. But there are actually other feasible shares that are incomparable. So for example, the MMS is not feasible, but it is known that the 3/4 of the MMS is feasible. So, and this share is feasible, but is not comparable to the Sn-1 share. So, sometimes one of them will be higher than the other and sometimes the other. So can we find one feasible share that dominates every feasible share? So we are searching for some share that dominates all other shares. If we can find such a share, then all agents will agree to use that share. And we prove that such a share doesn't exist. So the result with URI is that for additive valuation over goods, there is no feasible share that dominates all feasible shares. And actually, the result is stronger. It says that there is no feasible share that dominates all feasible shares that are nice. And I'll define that in a minute, including properties that relates to incentives that we call self-maximizing, and I'll also define it later. So dominating all feasible shares is impossible, and even dominating a subset of these all feasible shares that have nice properties is also impossible. Okay, so such an ultimate feasible share doesn't exist. What can we do now? So we're going to take the approach that we're going to search for some share that gives every agent a large fraction of the share that she will choose. So each one of the agents can choose arbitrarily a feasible share, and we want one share that will give all of them together concurrently a large fraction of that share, of these shares. Okay, so we say that share S rho dominates share S prime if after scaling down S prime by a factor of rho, so think about rho as say half, then S dominates S prime up to this factor of rho. And a row dominating feasible share is a share that row dominates every other feasible share. So say it's at least half of every feasible share if row is a half. Okay, so if the following observation is actually crucial because it says that for equal entitlement, a share dominates every feasible share if and only if it dominates the MMS. So in some sense, the MMS is kind of the gold standard of shares, of feasible shares for equal entitlements. And later in the next talk, Uri will discuss extending this to arbitrary entitlements. So what does this mean? It actually means that if you want to row dominate every feasible share, you need to row dominate the MMS. So MMS kind of like is our goal to find shares that row dominates the MMS. This will imply that we row dominate every feasible share. And for example, we know that we can 3/4 dominate every feasible share. The 3/4 MMS 3/4 dominates every feasible share. Okay, so this implies that we are actually interested in the best row such that we can row dominate the MMS. And there was a long sequence of works that tried to find the best row. Currently, it is known that it is slightly larger than 3/4, and it's strictly less than 1. And for small number of agents, say 3 agents or 4 agents, that there are actually better bounds that were proven. But you should keep in your mind that, you know, it's somewhere around 3/4 at least. Okay. So now if we are after a share that has nice properties, let's try to think what kind of properties do we want from our shares that will be used to make the decision about fair allocation. So the first property, as computer scientists, of course, we want polynomial time computability. So if somebody gives you a share, you should at least be able to check if the bundles that you got actually give you at least the promise of the share. For this, we need to be able to compute the share. So the first is efficiently checking that the assigned bundle is acceptable. The second problem might be try to computationally efficiently find an allocation that is acceptable, give every agent at least a feasible share. These are two different computational problems, and we want both of them to be polynomial time. Second, we want agents to report truthfully, so we want to share to have these properties that we call self-maximizing. This is different than dominant strategy truthfulness, and I'll discuss it in a few minutes. The goal of that is for agents not to need to strategize and for the allocator to have the correct input to compute the allocation, the share. And there might be other properties that you might desire. For example, continuity. If the evaluation changes a little bit, you don't want the share to change too much. And actually, these kind of properties are implied by self-maximizing shares. And I won't dive into it, but that's true. So a share is nice if it satisfies all these properties. And we are going to look for nice shares that row dominates every feasible share. Okay, let me briefly talk about this issue of self-maximizing shares. So we said that a share defines what's acceptable to the agents, but we leave it for the allocator to decide which acceptable bundle the agent is going to get. So any bundle that gives an agent her share is acceptable, and the agent doesn't know which one will be chosen. So should the agent report her valuation truthfully to the allocators that compute the share? So let's start with the MMS share. If you are asked to partition the items such that the least valuable bundle has the highest value, would you manipulate that partition and partition it in any other way? So I claim that actually it's not in your interest to partition it in any other way if you know that you're going to get the worst bundle, because you can only make the worst bundle worse if you don't partition it correctly. But this property doesn't extend to 3/4 of the MMS. So let's look at the example. Assume that we have n equal 2, so there are two agents, and we have an agent with valuation over 3 items. The values are 100, 80, and 20. So clearly the MMS is 100, and 3/4 of the MMS is 75. So the share guarantee of the agent with the 3/4 MMS is the worst bundle that gives her at least 75, and that bundle has a value of 80. So now let's assume that the agent actually manipulates, and instead of reporting the true valuation, reports a different valuation of 100, 50, and 50. Note that the MMS is still 100, so 3/4 of it is still 75. But with respect to this report, there is no single item that has value at least 75. So the allocator, in order to give a bundle that is acceptable, needs to give at least a pair of items, and note that each one of the pairs of the items has a value of at least 100. So by manipulating the report, actually, the agent gains. So we say that this 3/4 MMS is not self-maximized. Okay, so a share is self-maximizing if truthful reporting maximizes the share guarantee. Of course, this is measured with respect to the true valuation. So the MMS is self-maximizing, but 3/4 of the MMS is not self-maximizing. And actually, any raw fraction of the MMS, when rho is strictly smaller than 1, is not self-maximized. Okay, so let's
Moshe,
look at, yes.
can I ask you a question? So you said
Sure.
this is not like dominant strategy. Is this because the agent is not maximizing her own utility? We're not saying that the agent should find it optimal relative to her values to self-maximize, but sorry, to report truthfully, but relative to the maximizing the share guarantee.
Yeah, so she's trying to maximize the share guarantee. She doesn't know the allocation rule, so there is no fixed allocation rule
Okay.
in the mechanism, but rather there is only a share guarantee, and the agents actually are very afraid that they will get the worst bundle. They don't know which allocation will be used, and it's not with respect to one specific allocation rule. Thanks for the question.
Thank you.
Sure. Okay, so let's go back to the landscape of shares. We talked about the feasible shares, and then there are the self-maximizing shares. The 3/4 MMS is feasible but not self-maximizing. The MMS is self-maximizing but not feasible. And then there is this additional requirement from the share to be polynomial time computable. So, for example, the proportional share is polynomial time computable. You can see that the MMS is outside. It's not polynomial time computable unless P equals NP. We know that it's NP how to compute the MMS. But you see that I draw it on the edge because actually you can approximate it arbitrarily well. So in some sense, it's almost polynomial time computable. We are searching for a share in this intersection of the three properties. And we want a share that is both is feasible, is self-maximizing, and polynomial time computable, and rho dominates every feasible share. For rho, that is as large as possible. So, the 3/4 MMS, for example, we see that it's not self-maximizing, so we cannot use that share. We search for a different share that actually is self-maximizing and polynomial time computing. Okay, so our result, the result in this paper with Uri says that actually there exists a share that is feasible, it's self-maximizing and polynomial time computable. It obtains about 2/3 of the MMS, so it is 2/3 dominating, or more specifically 2n over 3n minus 1. So you see that this fraction is smaller than 3/4. But it is larger than half, and it's for a share that actually is self-maximizing. So in that sense, it's better than the 3/4 MMS result. For n that is small, for example, if n is at most 4, then the 3/4 improves, 2/3 improves to 4 or 5. And if there are only two agents, If there are only two agents, then the MMS itself is NP hard to compute. So the best that we can hope for in polynomial time is an approximation, and you can indeed get 1 minus epsilon approximation, or a share that is 1 minus epsilon dominating, that is feasible, self-maximizing, and polynomial time computable. So in a sense, that's the best that we can hope for. The general research challenge is understanding the limits of share-based fairness under incentive and computational constraints. Okay, now let me, in the few more minutes that are left, talk a little bit about best of both worlds results. So we talked about the possibility of using coin tosses in order to obtain something that is fair. So here's an example with two agents and two items. So one way to get the proportional share is toss a coin and decide who gets all the items. So say that we toss a coin, decide to give both items to Panda. I would argue that actually that allocation is not so reasonable in this case. And one of the agents might complain, and she would argue that she actually should get at least one of the items ex post. So in a sense, ex ante fairness guarantee is very weak, and you actually want an allocation that is not only ex ante fair, but also supported on allocations that have some ex post fairness properties. So just randomly giving all items to one of the agents, while ex ante fair is not ex post fair, and therefore the agent would not be satisfied with such a random allocation. So the best of both worlds approach is that we want concurrently to obtain both ex ante and ex post fairness. So ex ante, we want in expectation, say, to give every agent her proportional share, which is in a sense the best that she could hope for. And ex post, for every realization of the coins, we want to give some fairness properties. For example, we know that half of the MMS is a feasible share. So if we can give every agent half of the MMS, then they would get some fairness guarantee ex post. So in the example that we've seen before, instead of giving all the items to one of the agents, we might toss a coin and decide which agent gets the ball and which agent gets the corazon. And that, of course, gives every agent her proportional share. And also ex post actually gives every agent her MMS, because in this case, her MMS is the value of the worst item. So every item has value at least the MMS. And of course, this procedure itself is not the best that we can do. Maybe it makes more sense to do round robin in a random order. This actually would be better for both agents. Okay, so what can we show here? We can show that there is a polynomial time randomized allocation that give every agent her proportional share ex ante, and concurrently give her half of her MMS ex post. That is, the support of the randomized distribution is only on allocations that are half MMS. So that's best of both world results. And later in the second part, we will talk about best of both world results when agents have arbitrary entitlements. Okay, so let me summarize the first part of the tutorial. We are interested in fairness for indivisible items without the use of money. There are several notions of fairness that one can think of: envy-based and share-based. Unfortunately, the MMS is not feasible. We're interested in fairness, incentives, and computation. We cannot give all agents, there is no feasible share that is the best. Therefore, we will need to relax the goal, and instead of dominating all feasible shares, we want to give a large fraction of every feasible share. We are able to obtain a large fraction, not the best that is known, but a large fraction, together with incentives and computation. And we also discussed best of both world result for randomized allocations. These are allocations that gives both ex ante and ex post fairness. And in the second part of this tutorial, we will talk about extending the theory of share-based fairness and also a little bit about envy-based fairness to agents that have arbitrary entitlements. So that's it for the first part. I'll be glad to take questions.